Hello everyone. So recently I was discussing a USAMO problem with one of my students and I thought of sharing it with you. This problem is related to combinatorics and it is partially related to counting and as well as logic. So let's look into the solution and learn the strategy. So here is the question. This is from USAMO 1999 problem 1. It talks about a checkerboard which is of the dimensions n cross n. With the following condition, we need to place the checkers. Every square that does not contain a checker should be adjacent to a one that is containing a checker, and any given pair of squares that are containing the checkers should be possible to connect through sequence of moves along the adjacent squares which are containing checkers. Prove that at least n square minus 2 by 3 checkers are placed on the board. Let me give you an example through 5 cross 5 checkerboard. Suppose this is the 5 column, these are the 5 rows. Then supposing that the cross mark represent a checker, then this configuration would correspond to a valid configuration that satisfies the given conditions. Because if you consider any square, let's say this one, that is not containing a checker, it is still adjacent to a square which is containing a checker, satisfying the condition, and it is possible to connect any square with a checker to any other square that is having a checker through sequence of moves that passes through squares that has a checker. An example from this square to this square is provided, and you can take any two squares. For example, this one to this one, we can connect it like this. So let's call it as connected checker configuration. And in a connected checker configuration, we need to prove that there are at least n square minus 2 by 3 checkers. So how do we start this? So whenever you see a problem related to proving that at least these many number of objects or quantities should be there, then a usual strategy would be induction. But if you try to use induction in this particular configuration, then you would need to take a 4 cross 4 checkerboard out of this and apply the induction step on this to move to a 5 cross 5 checkerboard. But here on the boundary there are very few checkers, right? And hence we cannot extend it to a 5 cross 5 checkerboard. So induction will not be a good idea. Probably the second idea that one could come up with is grouping of squares. Maybe you can try to group the squares in 3, and there are n square unit squares in total, and if you are able to get that in each particular 3 block, let's call this 3 block to be a Tetris. Then this Tetris, if it contains a checker, then there are at least n square by 3 checkers, because there are total n square by 3. You can try to validate this using that idea, but still grouping them using Tetris is not an easy job. Some Tetris might not have a checker. Maybe you can think more on this and comment your ideas. But the third method that we are going to actually do now will be based on construction of configuration. Let's construct a configuration and let's see how many checkers need to be placed at least. So call a unit square to be good. Call a unit square to be good if either it is adjacent to a unit square containing checker, or it is a unit square containing checker. So either checker must be present on it, or if it is not present, then it must be adjacent to a unit square which contains a checker. Then that particular unit square is called as good. And remember, after completing our construction of all the checkers, all n square unit squares must be good, and that's what we aspire for. Under that constraint, think about the number of unit squares which would become good for the very first checker that you place on the board, and assume also that you are starting with an empty board. Let's again use this 5 cross 5 checkerboard. For the very first checker that you place on it, at most 5 unit squares become good. This is assuming that the unit square is placed in the center corresponds to 5, whereas when you place it at the edges, then it will be less than 5. So at most 5, and in this particular example these are the 5 unit squares that became good. Okay, this is for the very first checker that you place on the board. Now remember that we are going towards the valid configuration and we are going to constrain that all n square unit squares must be good. So let's go on to place the next checker and place the next checker in one of the adjacent unit squares of the one that was recently placed. If that is not possible, then you can place it on some other unit square which is adjacent to already placed checker. So let's say the checker is placed here, and now how many unit squares are additionally becoming good? This one, and this one. So we can claim that at most 3 unit squares are good, are becoming good. Whereas in the first move, at most 5 unit squares are good. This is for the very first. Whereas for the next move, it is at most 3 unit squares are becoming. And notice that this unit square had already become good and we should not count it again. And let's say the next unit square is like this. Again, these 3 unit square become. And if you continue the process, and also since the entire configuration is connected, you can always go from one unit square, starting from any unit square of that configuration to any other unit square of the configuration through these checkers by placing them adjacent as it is connected again. Because the condition 2 exemplifies that any 2 squares containing checkers can be connected through sequence of consecutive squares that contain checker. And that's what we mean by connected. By placing adjacent checkers, we can move to any desired unit square containing that checker. So thereby I can proceed to this unit square, and again this one became good, but now I will have to go to some other unit square, maybe here, but for that again I will jump here, and I will come here. So we are indeed pertaining to the fact that any unit square that is filled, that is going to be filled with checker, is always adjacent to a unit square which already contain a checker. Thereby at most 3 unit squares are becoming good. And then again we can jump from here to here and come to this unit square and fill a checker here. And then we can proceed like this, and after this we can jump here to fill this, and then back again here, and to here and here, and fill the last unit square. Thereby we completed filling everything, and now let's say totally there are k number of checkers. Then first 5 unit squares became good, and additionally the remaining k minus 1 checkers contribute to at most 3 for each checker, and this number has to be greater than or equal to n square, because we know that finally n square unit squares are good. So this implies 3k plus 2 is greater than or equal to n square, which implies the number of checkers on the board after this procedure must be greater than or equal to n square minus 2 by. So this completes the proof. Though this process is elegant, the strategy is not trivial and not prevalent. I hope you enjoyed the video. We will meet in the next video and discuss more. Thank you.